Formal charge is a concept that can be used to identify which Lewis dot structures are the best or represent the lowest energy or most stable forms of a molecule. So in this example, I'll be using thiocyanate, SCN-, has 16 electrons. Carbon's going to be the central atom, it's the least electronegative. And put the sulfur and the nitrogen around the outside, and we dump a bunch of electrons in. And the last step was to make an octet for the central atom by pulling electrons from peripheral atoms so that they're shared. But there's 3 ways we can do this. So we can pull one there and then a second set from sulfur and make a triple bond between the sulfur and carbon. We could pull one set from sulfur and one set from nitrogen, or we can pull both sets from nitrogen. Each of these 3 structures meets our criteria of each atom having an octet and having the proper number of electrons, an appropriate central atom. But they differ. Unlike the nitrite example where we had 2 equivalent structures and we drew a resonance arrow, one of these structures is significantly more stable and prominent than the other 2. And one way to find this is to look at a term we're going to call formal charge. And formal charge is basically an accounting system. It's a way to figure out where the charge in the molecule is located, which atoms have the appropriate number of electrons. And so the way we're going to calculate formal charge is the valence electrons minus the assigned electrons. So the valence electrons are relatively straightforward. Carbon has 4 valence electrons. The assigned electrons are a little messier, and the rules for how we assign electrons change. When we were talking about octets, all the bonding electrons that are shared with an atom counted. When we're doing formal charge, it's going to be all of the non-bonding but because we're effectively double counting the bonding electrons when we're doing the octet rule, we need to only use half of the bonding. Each atom gets half of the electrons that they're sharing. So in this case, carbon has no non-bonding electrons, and it has 2, 4, 6, 8 bonding electrons. Half of that is 4. 4 minus 4 is 0. So in this case, carbon has a formal charge of 0. And it has a formal charge of 0 in each of these structures. In each case, 4 valence electrons. That will always be the case for carbon. But 4 assigned electrons, half of 8 non-bonding electrons. Okay. Let's look at the nitrogen atoms. So nitrogen should have 5 valence electrons. In this top structure, we have 2, 4, 6 bonding electrons. And non-bonding electrons, and 2 bonding electrons. Half of 2 is 1, plus the 6 is 7. So in this case, this nitrogen is carrying a -2 formal charge. We move one structure down, the nitrogen should still have 5 valence electrons. It has 4 bonding electrons, half of that is 2, and we add that to another 4 non-bonding electrons, that's 6. In this structure, nitrogen has a formal charge of -1. In the bottom structure, 5 valence electrons, it has 2, 4, 6 bonding electrons shared with it. Half of that is 3, and we add that to the 2 non-bonding electrons is 5, or 0. So in this case, nitrogen has a formal charge of 0. Okay. In each case, nitrogen should have 5 valence electrons. The top structure assigns 2 more electrons than nitrogen contributed. It has an overall negative charge. It has more electron density than it would normally. Okay. If we flip over to the sulfur side, sulfur should have 6 valence electrons. 2, 4, 6 bonding. Half of that is 3. We add that to the 2. That's 5. This is plus 1. Okay. Erase that. This one comes out to 0. And this one comes out to -1. In each case, the sum of the formal charges of each atom must add up to the overall charge on the molecule. If you're explicitly writing the formal charge, you don't need to put the structure in brackets and put the overall charge outside. Now, in this case, this structure, I would say, has more charge separation than the other two. It takes energy to do that. This is less stable. That negative charge on the nitrogen wants to move over to the positive charge on the sulfur and release. This is the least stable of these options. Okay, so first of all, minimize the overall formal charge. If you can, pick structures with fewer charges. Okay, second thing to look for is where the charge lies. And these bottom two structures both have just that single atom with a -1, but it differs which atom that is. And when we're picking between these, we want to look at the electronegativity listed in the periodic table. And nitrogen has an electronegativity of 3.04, and sulfur has an electronegativity of 2.58. That 3.04 is more electronegative. Nitrogen more strongly pulls on electrons than sulfur. That's in part due to the smaller size. It's in part due to its effective, well, it's mostly due to its smaller size. This is the best structure. I'm going to, when I can, put the negative charge on the most electronegative atom or the positive charge on the most electropositive atom. So this is going to be the best structure because less formal charge than the top one, and the negative charge resides on the most electronegative atom.